Hello class, we're going to do our notes a little bit differently this chapter since I can't be there today. We're going to do our chapter 15 notes through this video. It's still the same PowerPoint, so please fill out your note sheets as I talk you through it. Chapter 15 is all about waves and their wave properties. So sometimes our energy sources, whether that be a light source or a source of heat or a sound source, sometimes those sources are in different locations than where we actually need them to be. So sometimes we need to find a way to transfer our energy by some sort of method. So we need to get that energy source to another location so that it can be as used for us. Kind of like if we make electrical energy in a power plant, we want to be able to then transfer that electrical energy from the power plant through the wires into our homes. So there's a couple different ways that we can transfer energy. One way is through an actual physical movement of material. This would be like a projectile, something flying through the air. Wind causes a movement of material and so on. One big example of this is when you throw a ball, that ball has energy. When that ball hits the window and maybe the glass shatters, the glass is going to shatter because the energy is being transferred from the motion of the ball to the window. So movement of material is one way we can transfer energy. Another way we can transfer energy is through thermal convection. Thermal convection, the term thermal makes us think heat. So in thermal convection, we are taking heat energy and we're transferring it. This is thermal convection, and the transfer of heat is the movement of quantities of heated gas or liquid between two locations. So like in the drawing here, if you open the oven door, the heat that's in the oven is going to transfer through the gas, through the air in the room, and you're going to feel that heat hit your face. It can also happen through liquids, like through water as well. Another way that we can transfer our energy from one location to another is through waves. And again, that's where our chapter is leading us. Some example of waves are sound waves. So anytime you hear a sound traveling, it's traveling in a wave. Light waves, the waves you see in water in the ocean, or also any waves that come from an earthquake, like seismic waves as well. Now, it doesn't really matter what type of waves we're looking at, sound, light, or water. The ideas that we talk about with waves and the language is the same for all of them. So what we're going to learn today with our language that we use for sound and light waves would be the same if we were to talk about ocean waves or earthquake waves, seismic waves as well. All right, so a wave. A wave is a disturbance that's going to carry energy from place to place. It's going to carry energy. It does not carry matter with it. It's just going to move the matter as it goes through it, but not actually move it with the wave. So a great example of this is, let's say you were at a baseball game. So here we've got a picture of people at a baseball game or even a soccer game, and they're going to do the wave, meaning we're going to start somewhere in the stadium. Everybody's going to stand up, woo, throw their hands in the air, and then sit back down. You're going to see this wave travel around the stadium, but the people in the wave don't actually run around the stadium with it. It causes you to move. You stand up and then you sit down, but it doesn't actually carry you along with the wave as you go around the stadium. So that's a good thing. You don't have to run around the entire field to make the wave happen. You just have to stand up and sit down as the wave of energy passes through you. Now, some waves have to have matter, which we call a medium. They have to travel through a medium. And some waves do not need a medium to travel through. They can travel through space, empty space, and the vacuum that's in space. If a wave does not need to travel through matter, meaning it doesn't have to travel through a solid or liquid or gas, it can just travel on its own, then those are called electromagnetic waves or EM waves. Electromagnetic waves can travel through material, so they can travel through the air, they can travel through water, they can travel through some solids, or they could travel through a vacuum. And that's what allows electromagnetic waves to travel through empty, open space, up in space. Some examples of our electromagnetic waves are visible light. So the light that you see, the light that comes from the light bulbs, the light that comes from the sun, the light that comes from stars, that is visible light. And again, it can travel through the air and the water and the materials we have here on Earth, so different mediums, but it can also travel through space. That's what allows us to see the light from the stars. Microwaves, radio waves, X-rays, infrared rays, and ultraviolet waves are also all examples of electromagnetic waves. Again, they can travel through a medium, but they do not need one. Now, electromagnetic waves can travel through nothing, but there are some waves that have to have a medium. There has to be some sort of material, whether it's solid, liquid, or gas, that they travel through. These waves are called mechanical waves. Sound waves are mechanical waves. Ocean waves and earthquakes are all mechanical waves as well. What that means, again, they have to travel through something. If you were up in outer space where it is a vacuum and you were talking and somebody was across the way, you weren't connected through any radio, or anything like that, you would not be able to hear anything. There's no sound in outer space because there's no air or medium for it to travel through. Here on Earth, you hear my voice because the sound waves are traveling from my mouth through the air, which is a medium, and hitting your ears. Mechanical waves can be transverse waves, longitudinal waves, or surface waves. And we're going to go through those 3 different types of waves now together. So there's 3 types of waves: transverse, longitudinal, and surface. Transverse waves are waves in which the medium or material they travel through is going to move at right angles to the direction of your wave. These are your typical waves. This is, if I asked you to draw a wave, this is probably what you would draw, that kind of squiggly line up-down motion. What happens is initially our particles are just sitting there flat. And when the wave passes through, those particles move up and down or side to side as the wave moves through in a different direction. So they're moving at right angles. As the wave moves left to right, then the particles are going to move up and down. There are some important parts of transverse waves. The first is the crest. The crest is going to be the highest point of the wave, just like if you were talking about an ocean wave and we were talking about a crest. The crest on an ocean wave is the highest point. The lowest point of the wave is going to be called the trough. And those are going to be important when we talk about a few more of our wave properties as well. Our second type of wave is longitudinal, also known as compressional. So we'll refer to it a bit both ways. Most of the time we'll use longitudinal, but you'll see here in a second why we also call them compressional. These are waves in which the medium is going to move back and forth in the same direction as the wave. So now instead of having a right angle, whereas the wave moves from left to right, the particles move up and down. Now instead, as the wave moves from left to right, the particles are also going to move left to right. They're going to kind of just vibrate back and forth as the wave passes through. A great way to think of this is like a spring or a slinky. If you were to just push the slinky, you're going to create these areas and you're going to see the wave move through because you're going to create these compression areas and then these areas where the slinky gets spread out. And those actually have names, compression and rarefaction, and they're the important parts of our longitudinal waves. Compression is where our particles in the wave are going to be closest together. So as the wave passes through, it's going to compress some particles together. That's our compression area. And then we also have rarefaction. Rarefaction is going to be where the particles are spread apart or stretched out. So for example, a sound wave is a compressional or longitudinal wave. And as the wave travels through, you're going to get these areas where the particles compress together and these areas where the particles spread apart. Again, the particle isn't traveling down with the wave. All that particle is doing is moving back and forth as the wave passes through it. So we get these areas of compression and these areas where they're spread out called our rarefactions. Our last type of wave are surface waves, and we're actually not going to focus on any surface waves. Surface waves like ocean waves and our seismic waves from earthquakes. They're what happens when the particles in a surface wave move both perpendicularly and parallel to the direction in which the wave travels. So it's kind of a combination of transverse and compression. And if you think of an ocean wave, oops, one step too far. When you're in the ocean and let's say you're floating in the ocean and a wave comes through, you're going to move up and down with the wave, but you're also going to move forward a little bit and then back. So really you're making this almost circular motion where you're going up and down, forward and back, up and down, forward and back. making a circle or an oval because you're moving both perpendicularly and parallel as the wave travels through. Okay, so that takes us through our introduction to waves and our wave types. In the second video, you're going to see the wave properties, and then we'll talk about how we can change wave directions as well.